So we're going to take a look at what our second derivative tells us. So a parabola is concave up if your first derivative is increasing, meaning your first derivative is getting more and more positive. It could be negative, but if it's going in the positive direction, basically it means if your second derivative is positive, then it's concave up. Concave up basically means it's a parabola opening upwards, or at least part of a parabola opening upwards. Now, your second derivative is when, if it's negative, it's concave down. And so if your second derivative is negative, your original graph is opening concave down. So it's part of a parabola going down or part of a full parabola going down. Now, graphs will switch from going concave up to concave down, part of a parabola going up to part of a parabola going down. And when it switches, that's called your point of inflection. Point of inflection occurs when your second derivative is either equal to 0 or undefined. So you're finding your same critical points by your derivative being 0 or undefined, but if it's second derivative, it tells you whether it's concave up or concave down. So here we have part of a graph that is concave up. Here is part of a graph that's concave up. And then here is part of a graph that is concave up. And now here are parts of the graphs that are concave down. But where you switch to go from up to down or down to up is what we refer to as a point of inflection. So all these red points where you switch from concave up to concave down or vice versa is a point of inflection. Your point of inflection for the most part is where your tangent line would start to or switch to the other side of your graph. Because your tangent line here would be to the left of your graph, here to the left of the graph. But over here, it's to the right of the graph. And so when your tangent line switches from one side to the other side, that's also where you can find your point of inflection. So let's go ahead and find all of our information for this problem here. We have extrema. Remember, extrema are max and mins. We get that from our first derivative. We have inflection points and concavity. That's all going to be from your second derivative. So we'll go ahead and we'll do our first derivative. Exponents in front, decrease by 1. Find our critical point, so we set it equal to 0 and solve it. So we're going to get a critical point here of when that's 0, which is 0, and a critical point here when x minus 3 is 0. In this particular case, we're not going to get any critical points from your first derivative being undefined because you have no variables in the denominator. So you're going to put these two critical points of 0 and 3 on a number line. Now, we got these critical points from your first derivative. So label your number line as your first derivative. So now you got to try a number in each region. So we try a number over here like -1. -1 squared we know is positive times 4 is positive. -1 minus 3 is a negative. A negative times a positive we know is a negative. Try a number in between like 1 or 2. Well, 1 squared is positive times 4 is positive. 1 minus 3 is negative. So a positive times a negative is still a negative. Try a number over here like 4 or 5. Well, whenever you put it in here, because of the squaring and timesing by positive is positive. But 5 minus 3 is positive. So a positive times a positive is a positive. So, if your first derivative is negative, that means your graph is going down. So it's decreasing, going down. Here, it's negative again, so it's still going down. Here, your first derivative is positive, so it's going up. Whenever you have bottom of a valley, then we know that that is a minimum. So we have a minimum when x is 3. But once again, how do you find the y value? Well, if you're trying to figure out the y value, and if you know x is 3, plug 3 into your original function, and that's where the negative 27 comes from. So here what's going on, it's coming down, leveling out with a slope of 0 because your first derivative is 0, and then continuing on down. That's referred to as a saddle point. So that would be like this here, it's a saddle point. Now in our situation, we're coming down, leveling out, and then going down. So that's an inflection point. Well, we have an inflection point when x is 0. How do we figure out the y value? Plug that into your original function. So we have only one extrema, and that would be here. Now we got to do all the inflection points and our concavity. So your first derivative may tell you some inflection points, but second derivative will always tell you inflection points, and your second derivative will always tell you concavity. So in other words, to find our second derivative, we just have to do the derivative of our first derivative. And we get this. Set it equal to 0. Well, you could factor it by pulling out a 12x. And then you could set each part equal to 0 because you have two things multiplied together to give you 0. So you would get critical points of 0 or 2. And now we're going to do a number line with these two critical points. So we'll do a second number line for our second derivative and put our two critical points on there. But because these critical points of 0 and 2 came from your second derivative, we label our number line as second derivative. Make sure you have all your number lines labeled, so it helps you know where to plug stuff into. Now, we're going to try number to the left of 0 here, like -1. But your number line's labeled second derivative, so you plug it into your second derivative. 12 times -1 you would know is negative. -1 minus 3 is negative, so you'd have a negative times a negative, so you know it's positive. Try a number in between, like +1. So 12 times a +1 in front would be positive. Put a 1 here, that would be a negative. Positive times a negative you would know is a negative. Try number to the right over here, like 3. 3 times 12 is positive. 3 minus 2 is positive. A positive times positive is a positive. So if your second derivative is positive, that means it's concave up. So like a full parabola or part of a parabola that opens up. If your second derivative is negative, it's concave down. So then we draw those shapes underneath. Second derivative is positive, so it's concave up. So we draw a parabola opening up. So whenever you switch from concave up to concave down or vice versa, it's a point of inflection. So we have an inflection point here at 0, which we knew from our first derivative over here on the left. So we plug in 0, because that's our x, plug it into your original function, you can always find your y. But we know we have a second inflection point because we're switching from concave down to a concave up. So if your inflection point has an x-coordinate of 0, to find the y-coordinate, plug in 2, or inflection point being x being 2, plug that into your original function to find the y value. Now it says concavity structure. That means they want to know where is it concave down. Well, it's concave down in between 0 and 2. So you write that. And you can do interval notation for that. Where is it concave up? Well, it's concave up here, and it's concave up here. To the left of 0, to the right of 2. So label your number lines, label your derivatives as either first derivative or second derivative. Have your number lines labeled. What's on top relates to your derivative. What's on the bottom describes what's going on with your function on both of these. So here we want to find extrema, inflection points, and concavity again. So we're going to go ahead and find our zeros, because that's going to help us when we're doing our sketching. To find your zeros, you set it equal to 0, and then you'd have to solve it. So two things multiplied together to give you 0. So set the first thing equal to 0, you get this. The second thing may factor, it may not, but it's quadratic, so you could always do the quadratic formula. If you do that, you would get this here. Well, those are some messy, ugly numbers, so you might want to have some approximations. So if you're doing a number line, you know, or graphing it, you know where to put stuff. So here's your approximations for when you are plotting them on a graph. So to find your extrema, remember we have to do first derivative. So we're going to take our original function up here and do our derivative. And then we got to find our critical points. Remember, your critical points are where your derivative is equal to 0 or undefined. We have no variables in the bottom, so no undefined. But now that it's set equal to 0, we can factor this. We can pull out our common factor of an x squared, and we can pull out a common factor of a 20. So what we have left in the parentheses may factor farther, may not. Being quadratic, if you can't factor it, always use quadratic formula. So what would cause the first part to be equal to 0? Well, that would be 0. What would cause the second part to be 0? So go 2x minus 3 is equal to 0. Solve that, and you get 3 halves. Set your last parenthesis equal to 0, and you would get negative 1. Those are your critical points from your first derivative. So then you have to do a first derivative number line, putting your critical points of negative 1, 0, and 3 halves on your first derivative number line. Label it that way. Then you could go ahead and try a number from each region into your first derivative because that's what it's labeled as. So try a number over here to the left of negative 1, like negative 2, plugging it in. Easiest to do it into your, come on, just a second here, into your factored form. So if you plug in negative 2 here, you know it's positive. Then you'd have 2 times negative 2, which is negative 4 minus 3 is negative. Plug it in here. And so we get a negative times a negative here times another positive. Well, that ends up being positive. First derivative then tells you either going up or going down. It's positive, so we know we're going up. Try a number in between, like negative 1/2. Negative 1/2 squared is positive. 2 times negative 1/2 is negative 1. Minus 2 is negative. Negative 1/2 plus 1 is positive. A positive times a positive is a negative. So it's negative. First derivative tells you you're going up or down, and it's negative, so you're going down. Try a number over here, like 1. 1 squared is positive. 2 times 1 minus 3 is negative. 1 plus 1 is positive, so we get a negative again, so you know you're going down here. So try a number to the right over here, like 2. Plug in 2 for x here. You get 4 minus 1, or 4 minus 3, which is 1. 4 plus, or 2 plus 1, which is positive. So everything's positive, so your first derivative is positive, which tells you your graph is going up. So we have top of a mountain here, so we know that that's a max. We have bottom of a valley here, so we know that that's a min. Here you're going down and then still going down. You're not a mountain or a valley, so it's a point of inflection. So to actually find the max and the min, we can take our x value being negative 1 and plug it into your original function. Inflection point. The x is 0. To find the y value, take that x being 0, plug it into your original function. Local min. Take your 3 halves, plug it into your original function to find the y value. And you would get this. Now that decimal is an exact answer. You could write it as a decimal, or I mean a fraction if you wanted to. So now that's your extrema. So first derivative tells you increasing, decreasing, and extrema, and some points of inflection. Second derivative tells you concave up, concave down, and all points of inflection. So to do our concavity and all points of inflection, we have to do our second derivative. Well, here's your first derivative. To do your second derivative, you put the exponents in front. decreasing by 1. Find your critical points by setting it equal to 0. Critical points, once again, occur where your derivative is 0 or undefined. This one does factor. So what would cause this here to be 0? Well, that would be 0. This here is quadratic. It may factor, it may not. If you can't factor it easily, use your quadratic formula. So in this case, it does not factor nicely, so we use quadratic formula, and we would get this ugly thing. Oh, gee, I have no idea what that really means for putting stuff on my number line. So I'm going to also look at the decimal approximations of those, so it helps you kind of know where to put those on my number line. So I just got critical points from my second derivative. So I'll do those critical points on a labeled second derivative number line. So I'm dealing with my second derivative number line, so I have to plug stuff into my second derivative. Take a number to the left of negative 0.7, like negative 1, plug it into your second derivative. Now, whether you would plug it in here or plug it in here would not make a difference. And in this case, you get negative. If your second derivative is negative, that means you are concave down. So it's part of a parabola opening down. Try a number in between here and here, like negative 1/2. Plug it into either one of these two, whether this one or this one, because we don't have anything fully factored. Remember, this was fully factored, so we could just see what each part was. Nothing's fully factored here, so we can't use that. So we're going to actually work out what the value is. And in this case, we get your second derivative to be positive here. So we know between here and here, where second derivative is positive, we're opening up. And then we continue to do that. We could try 1. 1's pretty easy to plug in here or here. And we get that to be negative, so we know between these two critical points, we're concave down. And then we try a number to the right, like 2. Be pretty easy to plug in 2 to either one of these two spots, and we would be getting a positive, so we know over here we're concave up. So notice we have a happy face here, and we have a sad face here. So for your extrema and your points of inflection, and your concavity. Concavity is where you are concave up, which would be between negative 0.7 and 0, and over here to the right of 1.07. Now, you should maybe be using your exact ones right here, but concave up is in between those two and here. Concave down would be to the left of negative 0.7 and in between 0 and 1.7. And once again, you could always use your exact values right here versus your decimal approximations. Inflection points is where you switch concavity. So we switch at each one of our critical points here, so each one of these is an inflection point. So take 0 and plug it in to find the y value. You've got to plug it into your original. And that 0, 0 we knew from our first derivative also. Then take your other critical point. You'd have to plug that into your original function, and we're going to get approximately that. Now, could you go ahead and plug in the exact? Yes, but I think that would be a royal pain in the butt to do, so we'll just do approximations. Take your other critical point, plug it in, and we would get that. So based on everything we get from our first derivative for max and min's points of inflection, concave up or increasing and decreasing, and then everything from our second derivative with inflection points, concave up, concave down, and our zeros that we had up here, if you graph all that precisely, you would then get this shape of a graph. So here we're just looking for concavity and inflection points, which all comes from your second derivative. Now, could you start out by doing the quotient rule here? Yes. I'm going to go ahead and rewrite it as a product rule, or because I don't necessarily have to go ahead and use a product because I'm not multiplying variables times variables, so I could just use simple power rule then. Put the exponent down in front, decrease the exponent by 1, chain rule derivative of the inside. So I would get this. Notice I need to have written here f prime of x equals. And then all I'd have to do is just go ahead, and now I have variables divided by variables for my first derivative. So to do the second, I'd have to do the quotient rule on it. Derivative of the top times the bottom, so there's the bottom, times the derivative of the top, minus the top, derivative of the bottom, so put the exponent of 2 in front, decrease it by 1, and then chain rule derivative of the inside, over the bottom squared. And then this would be my second derivative, so I should have this labeled as double prime of x. So notice here we could do some simplifying. We have a x squared plus 3 and an x squared plus 3, x squared plus 3. Everything has an x squared plus 3. You could take an x squared plus 3 out of everything, simplify what's left on top, and we would just get this. Your critical points from your second derivative or first occur when your derivative is 0 or undefined. A fraction will be equal to 0 if the top is 0. The only way the top is going to be 0 is if the parentheses is 0, which is differences of squares, so you get plus or minus 1, and that's when your derivative is 0. You get critical points where your derivative is undefined, so you got to look at what causes the bottom to be 0. Well, that would only be what causes the inside to be 0. Well, if you square something, you know that's positive, and add 3, that's positive. So there's no critical points from the bottom. By the way, if you did just do the quadratic formula on the bottom, you would have ended up getting i's. So that means you have no real numbers where you get critical points from. So looking for stuff from our second derivative, label your number line as your second derivative, put your critical points on, try number to the left of -1 like -2 into your second derivative. We'd actually have to work out what the top and the bottom is here because it's not a completely factored form. And in this case, we get a positive, so we know it's second derivative, it's concave up. Try number in between like 0. That's pretty easy to plug in. We get negative on top over a positive on the bottom, so we get a negative. So we know we're concave down because it's second derivative. Try number to the right like 2. Plug it in on top, plug it in on the bottom, and in this case we get a positive, so it's concave up. Switching here from concave up to concave down, so we know that that's an inflection point. But once again, to find the y value, you take that and plug it into your original function up here. And switch from concave down to concave up, inflection point, take your y value, plug it into your original function. So it wanted to know inflection points, which we just found in concavity structure. So it wants to know where is it concave down. Well, that's between the 1 and -1. It wants to know concave up, so that means left of -1 and to the right of 1. So we could write that. So if you did go ahead and graph this one accurately, you would get this graph over here.